In this lesson, we will learn about the trends in the periodic table, down a group and along a period. The first trend we learn is valence electrons. Now, what are valence electrons? Electrons in the outermost orbit of an atom are called valence electrons. And these outermost electrons play a very important role in the chemical properties of an atom. Now, when we go along the period, here we have taken the third period. First we have sodium, and we write the electronic configuration of sodium. The atomic number is 11 and the configuration is 281. So we see the valence electron, the number of valence electron is 1. Next we get on to magnesium, atomic number 12, electronic configuration 282. So valence electron in the outermost orbit 2. So valence electrons 2 for magnesium. Then it's aluminium with atomic number 13, electronic configuration 283. So the number of electrons in the outer orbit is 3. Then we have silicon with atomic number 14, electronic configuration 284. The outermost electrons, the number of outermost electrons is 4. So valence electrons 4. We go to phosphorus, which is 15. Electronic configuration 285. 5 electron in the outermost orbit, so valence electrons 5. And in this way you go through all the atoms. For sulfur it is 6, for chlorine it is 7, and for argon it is 8. So you observe that as you go along the period, the valence electron keep increasing. So on moving from left to right in a period, the number of valence electron increases from 1 to 8, like we have seen here, 1 right up to 8. And the first element in a period has 1 valence electron. If you see, this is the first element, it has got 1, and the last element always will have 8 valence electrons. And the last of every period will have 8 valence electron. Except in the first period. There is a bit of an exception in the first period. We have hydrogen, whose valence electrons are 1, and then in the end here we have helium, whose valence electrons are 2. So you need to remember here valence electron 2 and here valence electron just 1. Otherwise in all other periods the first element has valence electron 1 and the last element will have valence electron 8. Now let's see what happens down a group. We'll take group 1. In group 1 we have lithium, and the configuration of lithium we know is 2-1 because lithium has got atomic number 3. The valence electrons in lithium is 1, so we just write here 1. These are valence electrons. Sodium, atomic number 11, configuration, electronic configuration 281, valence electron 1, electron in the outermost orbit, so I put 1. Then we have potassium, which is 19, configuration 2881, outermost orbit 1, valence electron 1. So we have observed that for all elements in group 1, the valence electron is 1. Now let's get on to group 2. So here is group 2. We have beryllium, whose atomic number is 4. So configuration is here 2, 2. So number of electrons in the outermost orbit is 2, means valence electrons 2. Then we get on to magnesium, atomic number 12, electronic configuration 282, outermost orbit there are 2 electrons, valency 2. Then we have calcium, atomic number 20, 2882, valence electrons 2. So what have we observed in group 2? In group 2 all have valence electrons 2, and that is why elements in a particular group have similar chemical properties, because the number of outermost electrons is the same. So group 1 had 1 valence electron, group 2 had 2 valence electrons. Now we go to group 17. So for group 17, the first element is fluorine with atomic number 9, and now you see how many, 2 and 7. The valence electrons are 7. This is group 17, it's got 7 valence electrons. Then you have chlorine with atomic number 17 and configuration 287. Electrons in the outermost orbit is 7. Then we go to bromine, also 7. We go to iodine, also 7. So 17 group, the valence electrons are all 7, hence they have similar properties. Now for the 18 group, which is the last group, helium, valence electrons 2, neon, electronic configuration 28, valence electrons 8, argon 288, valence electrons 8, all have got valence electron 8, except helium, that has got valence electrons 2. This is the only exception in the group 18. 18 have valence electron 8, and because they have valence electron 8, they are inactive. They don't find the need to share loose electrons. They have a complete octet state. So this group 18 is sometimes called noble gases. So now let's just summarize the relationship between valence electrons and group. So if it's got one valence electron, it will belong to group 1. If an atom has got 2 valence electrons, it belongs to group 2. Now, if it has got 3 valence electron, it belongs to group 10 plus 3, and that is 13. If it is 4 valence electrons, it belongs to 10 plus 4, that is 14 group. If it has got 5 valence electrons, it belongs to 10 plus 5, and this is 15. 6 valence electron, it belongs to 10 plus 6 in the 16th group. 7 valence electrons, it belongs to 10 plus 7, which is 17 group. And 8 valence electrons, it belongs to 10 plus 8, and this is 18 group. Now this last group is a very interesting group. It is called the noble gases, or the inert gases, because since they have 8 electrons in the outermost orbit, it's an octet state, and when it's an octet state, it's a highly stable state. The atoms do not lose, gain or share their electrons. So the take from this is elements in the same group have same number of electrons, valence electrons, have equal number of valence electrons, and because they have equal number of equal valence electrons, they have similar chemical properties. Now for the next trend, that is valency. Valency are the number of electrons that are lost, gained or shared by an atom to make the outermost orbit stable. What do you mean by outermost orbit stable? If it is a first shell, it has to have just 2 electrons, and if the outermost shell is like the second, third or fourth, it should have 8 electrons in the outermost shell. Now let's look along a period what happens. So we first have sodium here with configuration 281. We know the valence electron is 1. So what will sodium do to gain stability? It has got 2 options. It loses 1 or it gains 7. So the option is to lose 1. So sodium will lose 1 electron to gain stability. Hence its valency is 1. Next, magnesium 12. Electronic configuration 282. Outermost electrons are 2. So magnesium will lose 2 to become stable. So now it has increased, the valency is now 2. Magnesium valency 2. Let's get on to aluminium. Aluminium atomic number 13, 283. So valence electrons 3, valency will be 3 because it will lose 3 electrons. Next we go to silicon. Silicon 284, valence electrons 4, it will share the 4 electrons and hence we call this covalency. This is 4. Then phosphorus 15, electronic configuration 285. Now valence electron 5. Now here something different happens. There are 5 electrons in the outermost orbit. So these will gain 3. So gain 3. Here we just write here they lose. Write all these lose electrons. This one shares. And now here all these will gain electrons. We get on to sulfur, which is 16, 286. So 6 electrons in the outermost orbit and it will gain 2. Next 17 for chlorine, 287. 7 electrons in the outermost orbit, it will gain 1. And in the end we have argon, which is 18. Configuration 288. It has got 8 electrons in the outermost and it doesn't need to gain nor lose. So 0, valency is 0. So if you notice the trend of the valency, it is 1, then it becomes a little more 2, then it becomes 3, then it becomes 4, and then starts decreasing now. 3, 2, 1, 0. So it first increases from sodium to silicon, it increases, and then the valency decreases. But a point to remember are these first here they lose electrons. The one share, and here they also sometimes share, but they here gain electrons. So on moving from left to right in a short period, the valency of elements increases from 1 to 4 and then decreases to 0. And to recollect, group 18 is called 0 valent because the valency is 0 and therefore they're inert, they're very less activity. They're called also noble gases. Let's see the trend of valency down a group. So in group 1, the valence electrons we know are 1, hence the valency will be 1. It will lose. In group 2, valence electrons 2, so valency will be 2. In group 3, valence electrons, we have group 13, valence electrons 3, valency will be 3. Then we have group 14, valence electrons 4. Here we have valency 4. We call it covalency because they share, if you have seen in carbon. Then you have group 15. All elements of group 15 have 5 valence electrons, and hence now their valency will be 3 because they will lose electrons. Here we have 16 group, valence electron 6. This will lose or will gain 2, not lose, they will gain 2. So total should be 8. Here 17, valence electron 7, they will gain 1. And here 18, valence electron 8, and it will 0 valent. So elements of the same group will have same valence electron and hence same valency. So elements in the same group have same valency. Why same valency? Because they have same or equal number of valence electrons. We'll now learn about the size of the atom and how it changes along a period and down a group. First, what is the size of an atom? It is the distance between the center of the nucleus and the outermost electron shell of an isolated atom. So here we have the nucleus in the center, and we want to know the outermost orbit, not the inner. Here we have, maybe it have one orbit here, and they may have another orbit here. Now the distance between the nucleus and this outermost electron cloud is called the radius or the size of an atom. Now it is measured in picometers because it is very small. The unit uses picometer, and 1 picometer equal to 10 raised to minus 12 meter. So 1, we call it pm, equal to 10 raised to minus 12 meter. So let's see how the size of the atom changes down the group. Here first I'm going to do group because it's a little easier to understand, and then we will go for the period. So we'll take group 1, we'll draw the atoms of group 1, and we'll see what happens to the size. So the first one is lithium. It has got configuration 2,1, so it has got 2 shells, K and L. So that's nucleus. So it's got this K shell here and the L shell out, 2 shells. When you go to sodium, it has 3 shells, K, L, M. So you definitely expect the atom to be larger. So you have the K shell, then you have the L shell and the outer M shell. So here was K and L, this is K, L and M, this is sodium, lithium. Now we go to potassium and it will be even larger. So I'll just draw part of it. Now it is K, then L and then the M shell. So K, L, M, 3 shells. K, L, M, oh no, there's one more, N, there's another shell here. K, L, M, and they have a N shell too. So it's even larger. So what you expect the size of the atom to be as we go down the group? The size of the atom increases because number of shells keep increasing. Here again for second group, beryllium, two shells, K and L. So if here would be K and then there would be L. Then next we go to magnesium. It has got three shells, K, L, M. So you have K, L, and then M. And then we go to calcium, K, L, M, and N. Four shells, K, L, M, and N. So as you go down the group, the size of the atom increases, because the number of shells increase. So as we move down the group, the size of the atom increases as the number of shells increase. So down the group, like you have the smallest atom first, and then you have a little larger one, and it becomes even larger. Size of the atom along a period. Let us see what happens to the atom as we go along the period. For that, we'll take up the second period. In the second period, the first atom is lithium. And remember, we are dealing with the second period, so all of them will have just two shells. Here is the nucleus with these two shells. One, the K shell, and then the L shell. So the outermost shell is the L shell. Same when we go to the next. The next we have is beryllium. Again, we have the nucleus in the middle, and then the two shells, the K and then the L shell. Then next, after that, we have the boron, nucleus, two shells, K shell, and then the L shell. Again, here we have the carbon with the K and then the L shell. So if you go up to all of them till the end, you have the central nucleus, and then we have the two shells. So all these atoms in the second period have two shells. So you will expect the atoms to be of the same size, but that's not what happens. So now in the next figure, I have drawn only the outermost orbit. This is the second shell. This has got one electron in the outermost shell. This here has got two electrons in the outermost shell. This has got three electrons. The carbon has got 4 electrons in the outermost shell. This has got 5. Then this has got 6 and 7. The central nucleus in the first case has got 6 protons. So the outer shell is being pulled by 3. It's got 3 protons. It's been pulled by 3 protons. Now when we go to the next here, in the central nucleus you have 4 protons. Then in this nucleus here you have 5 protons. Next you have 6 protons. Then there are 7 protons. Here there are 8 protons. And last we have fluorine, which has got 9 protons. Now in beryllium, the outermost orbit is pulled by 4 protons, because there are 4, the nuclear charge is 4. Then the outermost orbit is now pulled by 5 protons. Here the outermost orbit is pulled by 6 protons. Then this is by 7 protons. This is pulled by 8 protons. And here it is pulled by 9 protons. So what do you expect the outermost orbit to remain the same or to shrink. We have seen that the effective nuclear charge keeps increasing. Effective nuclear charge on the outermost orbit increases as we go down a period. So definitely the atom size will not remain. If this is the atom size in one here, in the next one the atom size will decrease because now the outermost orbit is experiencing a stronger pull, and then it will further decrease because the pull is even more, and then further decrease. So as we go down the period, we find the atomic size decreases. I mean along a period, not down a period. This is along a period. The atomic size decreases because the effective nuclear charge, the charge on the outermost orbit, keeps increasing as the nuclear charge keeps increasing. So here's a summary of the